So one thing I want to show before we get started is over here, programming practice, no, teaching exams. Here we go. So this is an entrance exam to the Computer Science Graduate School for University of Tokyo, or Todai, which is like one of the most prestigious universities in Japan. It's a written exam, blah, blah. Basically, you have to take an entrance. The country works off of entrance exams for universities. So you've got a bunch of questions, and they post what they had in previous years. Now, blah, blah. Great. So first one is a math problem that if you study up on your math actually probably isn't so bad. Because it just deals with linear algebra, Cauchy-Schwarz inequality. I remember learning that. This is all stuff I learned at some point. They have a very strong mathematical bent. That's just the way it is. Problem 2 has to do with non-deterministic finite automata, which is something you'd learn in automata theory if you want. So not necessarily, right, completely above. It's not as hard as it looks. Basically, it's saying, we can start from here. We have you can transition to this state. If you see an A, if we see a B, we'll go here, or we could go here. So a non-deterministic finite automata basically means that we could have two edges that have the same output. So B could go here or here, and C could go here or here. But basically, it's a state machine, meaning that there's no memory involved in saying what kind of words can be determined, and then but anyway, it's not nearly as bad as it seems, again, because if you take that class, it's not really that difficult once you get a hold of it. But the reason I'm bringing up this entrance exam is because of problem 3. Consider the problem of sorting an array of integers using the heap sort algorithm. Assume the heap sort brings the minimum element to the front. In other words, that heap sort, sorts things from the smallest to the largest. Answer the following phases. Heap sort consists of 2 phases. Explain is what to be performed in each phase. So with heap sort, you have the heapify, and then you have the sorting phase. Consider sorting the following array using the heap sort. Draw the tree structure of the heap just after the first phase. So in other words, heapify it and then draw the resulting heap. Answer the time complexity of each phase when sorting an array of length n. Explain the reason. Well, it takes O of n time to heapify something and then n log n time after that. But basically, these are just questions that explain why you would want these to use the execution time with heap sort on modern computing systems is often longer than other sort algorithms such as quicksort or merge sort when sorting a large array. Explain a possible reason. Well, n plus log n takes longer than log n time with quicksort because quicksort normally is, on average, n log m with a constant in front. Normally does pretty well. Whereas merge sort is, again, always n log n. It's never going to do any better or worse than n log n. But with a large array, you do have to heapify for the array. So that does add in a bit of extra time there, right? So these are kind of questions that basically that again, and you could answer the vast majority of this section based on just this class. It's not necessarily there. That's a hardware question, but as you can see, it's always basically seems to be math question, hardware question, math question, automata question, a data structures question, and hardware question. By hardware, I mean circuitry. So but anyway, as you can see, this class basically means you can get a quarter of that exam of this high-end exam right, and these other things aren't actually too bad if you end up going that thing, and you don't necessarily have to learn the mathematics unless you're like planning on going to grad school, and most of the time with grad school they'll teach you the mathematics when you get there anyway. But anyway, I just wanted to point that basically that let's see if we look at 2016. Right? All I did was just modify the URL. If we look at their data structures question, right? See, it's a matrix question again, automata question again. Oh, this one's on binary search trees. Apply the following operations to the above tree. Insert 3, insert 8, delete 4, and delete 9. This should give you an idea of what they consider to be the relative difficulty of the other ones, right? It's not, they only look scary because they have scary drawings that you haven't learned about yet, right? It's the same reason that physicists use I'm half convinced that physicists use Greek letters. It's to make everything look scary and foreign and more advanced. But, depict a tree with a minimum height and maximum height for 7 nodes. Balanced binary search tree. Those kind of things. So this really isn't too... So the things you learn here are actually, things that we care about as computer scientists because they're the underlying ways of which we organize data. There's a reason we teach stuff in this class. Now let's go ahead and look at the second practice exam. Okay? So I'll go ahead, and I am recording this so that you'll be able to reference it later. There will again be 105 points. Again, this exam looks longer than it actually is because I have a bunch of extra practice pages in here, and also because when I give you a question where I ask you to draw something, I give you a lot of space to draw on it because, you might realize, I need to scribble it all out. Same with coding. I need to scribble it all out. Like, this question over here, which we'll get to, question 16, can be solved in like 4 lines. Is full, not necessarily, and same with equals, but the point being is that a lot of these can actually be, I give you a lot of space for a lot of these questions. All right, so I will go ahead and just mention the way these work. Okay, so the first page of the exam will be exactly like this page, except, the questions will actually be different. Okay, there will also be a question page like this on the final exam, just with the extra, just also with the graph data structure as well. So here we basically just choose the data structure that you think is the best. If you explain, so you get full credit for getting the correct one, but you can also explain your answer with no more than a sentence. No more than a short sentence, please. And if for some reason if basically your wrong answer makes sense with your explanation, I will either give you half credit or full credit depending on the strength of that argument. Okay, so 1, you need to model which patient should be seen next at a hospital. Patients should be seen in as close to the order of arrival, but patients in a more severe situation should be seen first, right? The person who's dying and bleeding out should probably get medical attention before that broken finger, even though that broken finger's been waiting for a while. So what data structure should we be using there? Priority queue. A router needs to hold packets in a buffer and deal with them in the order they appear. A queue. Queues are basically the data structure we use for buffers, right? Data comes in, we want to process it in the correct order. We use a queue. We need to model some kind of hierarchy. That's kind of a key word there. Which data structure is hierarchical? Tree. It's also a very hard word to say for me, hierarchical. All right, you need a data structure to hold your previous decisions in case you need to backtrack. I will tell you that a common wrong answer I've gotten for questions that are like this is recursion. That is definitely not, recursion is not data structure. Stacks. If you're backtracking, if you need a backup, you want to use a stack. You can make, so a wrong answer that can be turned into a correct answer here is a linked list. By saying with a linked list, we can backtrack, but we can also go forward, so that would be better. So that gives us more utility, and I'm like, okay, I'll give you that, right? No problem there, right? But with a stack, the entire point of it is doing a backtracking operation. All right, so this trees, relations, and vocabulary page, it's not going to be like this page. It's going to be actually like that quiz you took on tree operations. In fact, the quiz I gave you was was from the exam last spring. not this previous spring, but spring 2018. That was what was on there. So, so you can review that quiz if you want to see what this page is going to look like. But so this is just to help you review things. Answer the following vocabulary questions. The note at the top of the tree is called what? Root, right? Because computer scientists are terrible gardeners. Or maybe we're just gardening in 0G. The links from a node to its successors are called what?
The actual link.
Yeah.
Or
Oh, okay, technically. What?
ancestor.
Branch. So yeah, I accept branch, edge, link. Even though yes, that is self-definitional there. But basically, there's a lot of terms we can use for those, but a lot of them are also correct. The predecessor of a node is called what? The parent, right? And if your nodes with the same parent, what are you? Siblings, right? What is my parent sibling called? Uncle or aunt. It's not a formal name, but everybody uses that terminology, right? Your parent sibling is your uncle. Same with grandparent. You can, if it makes sense in a family tree, then you can make sense in a tree. I just highly recommend that anything beyond grandparent, you just simply go generic and call it ancestor, right? So describe without using code how to calculate the height of a tree recursively. So what is my height? So a tree's height, right? So here I am. I have a left subtree x, which is a height of x, and a right subtree, which has a height of y. What is my height?
Everyone's great.
Whichever one is greater, plus one. The height of a tree. So the height of a tree or a subtree is equal to the height of its bigger of its big. You calculate the height of its left tree and its right tree. Figure out which one is bigger, and add 1 to it for yourself, right? So why do I ask this? Because I'm kind of interested on that on the exam. So, okay. So draw an example of each of the following binary trees. Use a different example for each possible tree. Again, so the reason I want a different example is because if I draw this, is this a full tree? Yes, technically is, and we're all about technicalities here. So technically correct is the best kind of correct. So we've got, this is a full tree. Is it perfect? It's a height of 1, and it has 2 to the 1 minus 1 nodes in it. So it's perfect. Is it complete? Yes, it is. This is both full, complete, and perfect, which is why I asked you to do a different one.
So we get one freebie.
For one freebie. Well, on this exam, I do it. On the exam, I say, given this tree, please add nodes to it to make it to change it into X, right? Or if you remove these nodes from it, it will become what? Right. So a full tree. Let's just review. You're full if every node has 2 parents. If every node has 2 children or no children. So this is a full tree over here because every node has 2 children or 0 children. But as soon as we do this, that is
The perfect tree.
that's not. So it's not perfect because we don't have a node over here. For it to be perfect, it needs to be the tree has to be of height h with 2 to the h minus 1 nodes in it. So this is of height 3, right? So 1, 2, 3. Height 3. Its height is. So that means that for it to be perfect, it needs to be height 3 with 7 nodes, and there's only 6 in it. And if you notice, there's one more space for it to fill up for it to be perfect. So perfect means basically Perfect is defined by basically, you know, we all know what a perfect tree looks like. It's easy to that mathematical definition basically says, hey, here's a perfect tree of height 3, a perfect tree of height 4, looks like this. Basically, all the leaves are on the same level, and the level above that is completely filled with the children, and the level of that above that is all completely filled with their children.
Oh, but it would be a complete.
It is.
Oh, if it was missing the one.
This one wouldn't be complete. Complete is the most difficult one I find for students to understand. It has to go. It has to be filled from left to right. So to amend this, this is a complete tree over here. It's not perfect, but it is complete. This is no longer complete. But if I add a node here, it is complete. Yes?
I think it's easier to think of complete, like, could I use this in a heap?
Yeah, can I use this in a heap? That is an excellent way to put it. If you can use it in a heap, it's a complete tree, because there won't be any gaps when you're counting from left to right. Okay. So this question is going to be exactly the same minus the actual, numbers there. But essentially what I care about is when you draw stuff is the end right answer. But of course, if you do it part by part, you can get partial credit if you mess up somewhere. Also, I'm not too strict on that. It's just generally, if you mess up somewhere and accidentally put one node where it's not supposed to, has it been there the entire time? If you put one node on the chalkboard, been there on the chalkboard?
Yes.
Well, it's been camouflaged. Thank you. All right. So if you accidentally mess up somewhere, you'll probably just miss a point. If I can see that it's obviously just a mistake, you obviously know how adding an item to a tree works. I always think maybe I should remove this problem, and then somebody in my class of 40, 60 students gets it wrong, and so I'm like, it's a good question still. So, okay. So first thing we do is we put 42. We add that as the root. Then 10. 10 goes to the left because it's less than 42. 50 goes to the right because it's greater than 42. Then 12. 12 is less than 42, greater than 12, greater than 10. So 12 goes over here. 17, less than 42, greater than 10, greater than 12, so 17 goes over here. Right? 80 is next. So 80 is greater than everything in the tree, so it goes all the way to the right. Next is negative 12, which is smaller than everything in the tree, so it goes all the way to the left. Then 100 is greater than everything in the tree, so it goes over here. 96 is greater than 42, 50, 80, but it's less than 100, so once we get to 100, we pivot to the left over here, put that in. Right, making sense to everybody. This is what the question is doing. I think I have less of these on the actual exam. 86 goes, 86 is greater than 80, less than 100, less than 96, 86 goes over here, and then 72, greater than 50, less than 80, so it goes over here. So those are so that would be the answer to that one. Now, on the actual exam, I don't do using your previous answer, draw what happens when you remove. Instead, I give you an actual tree to remove, but I do have the whole, given this tree, please remove items from it. So draw what happens when you remove the following: 42, 12, 17, and 96. So, to delete 42, 42 has 2 children. So to delete it, we choose the next in order predecessor. The biggest thing that is smaller than 42, which we go 1 to the left, all the way to the right, we find 17. So we replace 42 with 17, and then we delete 17 from this tree, from the left subtree. Next, we delete 12. So we find 12. Does 12 have any children? Nope. So we can just remove 12. Next, we want to delete 17. which is the root, has 2 children. So we want to replace it with the next thing that is the thing that is the largest thing that is smaller than it, next in order predecessor. So we go 1 to the left all the way to the right, that gets us to 10. So we replace 17 with 10, and then delete 10 from the left subtree. So deleting 10, what we do is that we just simply have its child become adopted by its parent. And then 96. Delete 96. Again, over here, we're just deleting something that has 1 child. So again, the thing we're deleting, its parent adopts its child. So 100 will simply adopt 86. So you will be tested on all 3 cases, deleting a leaf, which is pretty easy, deleting a node with 1 child, and deleting a node with 2 children. All right. Which of the following is the pre-order traversal of a binary tree with subtrees left and right? Okay, which one goes for which is the pre-order traversal? Which of these options represents a pre-order traversal? Sorry? Pre-order. So that would be B, the root node first. With pre-orders, the root node first. In order produces it in order. Post order produces it with the last node. So let's go ahead and do a pre-order traversal of this tree over here. So here we do the root first, then the left subtree, and then the right subtree. So let's go to the left subtree. Left subtree is -12. We do -12 first, then we do its left subtree, which is nothing, and its right subtree, which is nothing. So we finished the left subtree of 10, so now let's go to the right subtree. So here we do 50 next, because we do pre-order traversal on the subtree, and that says do the root first, do the left subtree, which is nothing, then do the right subtree. So let's do the subtree that's represented by 80. So we do handle 80 first, then we do its left subtree, and then its right subtree. So 80's left subtree is 72. It's the only thing in it, so it handles itself, then it's left and right. Then we go to 100. 100 says I'm going to handle myself first, then I'm going to handle my left subtree, and then I'm going to handle my right subtree. This contrasts with in order, which says I'm going to do my left subtree first. So 10 says I'm going to process my left subtree first, then myself, then my right subtree. -12 says I'll do my left subtree, nothing. Myself, my right subtree. Then 10 says I'll handle myself, then I'm going to do my right subtree. 50 says I'm going to handle my left first, which is nothing, then I'm going to handle myself, and then I'm going to do my right subtree, which is 80. 80 says I'm going to do my left subtree, I'm going to do myself, which is 80, and then I'm going to do my right subtree. 100 says I'm going to do my left subtree, 86. I'm going to do myself, 100, and then my right subtree, 105. Now post order, right, this is the next question. Which order is post order? Not D, C.
Right.
Do the left, then the right, do my left subtree, then the right subtree, then myself. We know that 10 is going to be the very last item because it's all the way at the root. So for this one, I say do my left subtree, then do my right subtree, then do myself. 12 says left subtree, right subtree, myself, -12. 10 says do my left, now I'm going to do my right. 50 says do my left subtree, then do my right, which is nothing, then do my right subtree. 80 says do my left subtree, which is 72. 72 says I'm going to handle myself, or my left, my right, then myself. 80 says I handled my left, now I got to do my right. 100 says I've got to do my left, which is 86. Then it says I got to do my right, which is 105. And then 100 says I've got to handle myself. Okay, 80 says I've done my left, my right. Now I'm going to be able to handle myself. 50 says I've got to handle my left and my right. So I've handled my left, I've handled my right, so now I can handle myself. And then 10 goes, I've handled my left, and then I've handled my entire right subtree, so I'm going to handle myself. Notice that basically on this right side, we have basically 105, 100, 80, 50, 10. At the very end is that just big recursive chained call up there. This, again, like adding to the tree, it's going to pretty much be on the exam as well, just with different numbers. Draw the min heap that forms after inserting the following integers. 8 first, and you can ignore the underlying array, which means you don't have to actually draw the underlying array. I want you to draw the tree structure. I don't want you to have to spend time drawing the array. So again, this is being done by adding items to a heap, as opposed to heapifying an array. When we heapify, we move from the back and basically bubble items up. Here, we're going to just simply push items. We're just going to add items to an array, or to the heap. 8, then 10. 10 is heavier than 8, so it stays at the bottom. 50 is heavier than 8, so it stays there. 12 is heavier than 10, so it stays there. 1 is lighter than 10, so it's going to swap with 10 and bubble up. Right? Think of these as weights, where the higher weight sink down and the lower weight sink up. 1 is less than so it bubbled up. 1 is lighter than 8, so 8 sinks down while 1 bubbles up. Next is 4. Right? We always go left to right across the levels, and then start a new level as needed. So 4 is lighter than 50, so we swap. And then 3, and then it can't bubble up anymore. And then 3 is lighter than 4, so we swap. And 3 bubbles up over here and stops. So there we go. When we check, we can check our answer. Is 1 less than everything in the heap? Yes. Is 8 less than everything in its heap? Yes. 3? Yes. And then these guys are obviously the only items in their subheap, so they don't really care too much. Okay. Any questions? Does anybody need me to add a random item to this heap to see what would happen? Okay. Obviously, if you're adding to a heap, you're going to remove from a heap. So draw the heap after removing an element twice, right? So to remove an element twice, what are we going to do? We can only ever remove from the top of the heap. So what we do is we take this item and move it up to the top during our first removal, and then we have it sink back down. What about 4 and 3? 4 and 3 will swap. And then what about 4 and 50? 4 is lighter than 50, so it's going to stay put, right? Next we want to remove again. So 50 goes up to the top. Okay, we've got 50 and 4 and 8. What we want to do is that we want to swap with the smaller item. The smaller item should bubble to the top, because if 8 were going to bubble up here and we'd swap 50 and 8, then 4 would still be over here, and we'd get 8, 4, which would be invalid. So we swap with the smaller item, because otherwise we'll get an invalid state. 4, 50. 50 can't sink any further because it's hit bedrock. Right? There's nowhere else for it. It's as low as it can go. Okay. Huffman coding. This question will appear on the final exam as well as the second exam, just with the same kind of, just with different numbers, obviously, and different letters. Okay, so over here I've got APLE, so obviously I'm going to have you do apple. And then we have a random X thrown in. I try to make the math fairly simple. So what we're going to do is we're going to draw the Huffman tree for this symbol, for these symbols. So let's put them in order. X is a weight of 1. L appears 20 times in this document. P appears 40 times. A appears 50. E appears 60. Right? So now we've got to put it together in the Huffman tree. How do we put it together in a Huffman tree? We take the last 2 nodes. We take the first 2 nodes of the list and we combine them. So X and L get combined into XL, which has a combined weight of 21. X goes on the left because it was first. So this is a combined weight of 21, and we'll put 21 over here. Now here's the big thing that people often get wrong. Now that we've put it back into the heap, because it's a heap, it needs to resort itself. So 21 will go to the front of the priority queue. The priority queue, right? So now we do 21 and 40. So 21 goes on the left, the P goes on the right. Why? Because the combined one was the first item, and the first item always goes to the left. P was the second item, so it goes on to the right. And so now we combine it into XLP, which is a combined weight of 21 plus 40, which is 61. Okay, now we get into an interesting state. We have A and E. So A, E, A should go on the left, E should go on the right. Then they combine into AE with a combined weight of like 110. Okay? Now we've got two nodes left. We remove them both. This one goes on the left, this one goes on the right because the lower weight one was first. And so now they've combined into one tree. Not to scale, really, right? This one's, obviously this subtree is bigger than this subtree, but.
And why wouldn't you just do XLP and A?
Because of the ordering that happens. Unless I messed it up terribly.
Wait, no,
What?
wouldn't you have the XLP, the total 61 and 110, so it's 171?
Yeah, so the combined weight over here is 171 because that's everything added together. The weights, yeah.
No,
So let me reverse the steps, right? So how did we get here? We had XLP and we had AE. Okay? How did we get to AE? With 110 and 41 over here. Or 61. How did we get here? Well, A and E were first in the priority queue. A and E were first in the priority queue with combined weight of 50 and 60, which is so we took care of these two first.
Yeah.
Right. Every time you put the combined weight back in, it needs to go into the sorted order. All right. So regardless of the tree that you, I always try to be a super fair grader, which means that regardless of how appalling and abominable the tree you draw in the above part, so long as the format for a Huffman tree is correct. In other words, so long as that all the leaves are letters, right, and there's no letters inside nodes, then I will just simply use the next answer as though you had got it right. Because occasionally we get issues with students like they accidentally transpose two things, like they accidentally put the thing that should have gone on the left on the right, or they mix up that basically zeros and ones should go, that the zeros go on the left and the ones go on the right. Whatever, those are minor things. What I care is, do you understand the algorithm? So for encoding something right, we label all the edges with 0, that are all the left edges with 0, and all the right edges with 1. So to encode, and so if we were to make a table, A would be 1, 0, P would be 0, 1, L would be 0, 0, 1, and E is 1, 1, and then X is 0, 0, 0. And the big thing to note about this is note how that we've got a number that A and E, which are very high frequency compared to the other ones, they only take 2 bits of information to complete. Same with P, only takes 2 bits of information. But X, which rarely appears, takes 3 bits. And L, which appears sometimes, takes 3 bits as well. So the more frequent items have lower bits that are used to express them. So encode the string apple into binary using this encoding. So A is 10, P is 01, P is 01, L is 001, and then E is 11. So there you go. That's apple according to this. All right. So coding. Almost all the coding is going to be over basically these coding questions. I believe I do. I want to say I do. I'm trying to remember if you guys have 2. I can't remember if you guys have 3 coding questions or 4 coding questions, and I think it's 3. One of which is actually a 2-part question. So where basically you complete half the problem in one. You complete a function and then use that function in another one. All right. So there's not too much coding, but there's although it is one where I can thank the Department of Homeland Security for that question. So that's fantastic. You'll figure out the story as I give you the story there. So write a method given the root of a tree or subtree, computes and returns the number of nodes in that tree or subtree. You cannot use the size method. Forget it even existed. So let's go ahead and start over here with Geany exam.java. And I'm just going to make stuff up, but here we go. So public class exam, and for this to actually compile, because I'm sure you're going to be upset if it doesn't compile, we need to do a private class node, private static class node, which has which we don't need a constructor for. It will just simply, actually we do. We have private node. I wonder if that works. Private E data node E left node E right, and then public node E data is, and then we say this dot data equals data. There we go. There's our node class that we can now use it in methods. So here what we'll do is that we'll say,
You don't care about that in the exam, right?
no, I'm just doing this for coding's sake, so that if you're coding it up on your compiler, it's not going to happen. So now the size method, which I'll just grab over here. Public static E int size tree, which returns the size of the tree or subtree. Right? So the way these problems always work is we ask ourselves, is that we always want to check if root is null first. That's almost always a base case for us. If root equals null, right? Again, you want to always check your base cases. Hold on a second. Properties. Edit preferences. Display interface editor. Viewer code. Sorry. And then okay. So there we go.
And so there we go. So if root is equal to null, then what is the size? If the tree doesn't exist, what's the size of the tree that should be returned?
0.
Yep, return 0. Okay, otherwise, the tree exists somewhat. So what I need to do is that, in that case, I need to say, I need int left is equal to whatever the size of the left subtree is. So I ask what the size of the left subtree is, root.left. I ask what the right side, the size of the right subtree is, right, is equal to size tree, root.right, because there's no other recursive case. If the tree is empty, then its size is 0. Otherwise, it's myself plus whatever the size of the left and right side tree is. And then I will return 1 for myself plus left plus right. And yes, we can actually just condense that into the following statement. Return 1 plus size tree root.left yes.
Could we just do like the if and then else return the 1 plus and then size both sides?
Yeah, that's what I'm doing over here. Plus 1.
Because the return takes it out of the method otherwise in the if statement.
Yeah.
Yeah, well, this is more just because you didn't do that else, but
I don't need the else because the return will stop it. I mean, I can also do it just as for fun. I can show you guys that as one line, you can do it like this. Return root equal null question mark 0 colon.
Is it just gonna throw an error?
is that a lambda?
It's legal, I'm pretty sure.
Nope, it is legal. It is legal. It is a ternary statement. It is a one-line if-else that you should never use because its readability is terrible. It says if this Boolean state, so basically it works, the way it works is basically that it is Boolean, it is a Boolean followed statement followed by a expression 1, then colon expression 2. And what it says is that if the expression is if the Boolean statement is true, then the value is expression 1. Otherwise, the value is expression 2.
Computationally, is it the same amount of work for both of them?
I have no idea.
Okay. Wait, so what's the exact name? That's not
That
lambda.
that is a ternary that is the ternary operator.
Okay. Are we
And-
ever gonna cover the lambda?
Not really. I can try teaching them myself that in Java. I don't know them too well in Java. I know them plenty well in Python. But and I'd be more than happy to teach you that.
I'll learn
Python, I can go over that with you. But all right, so that one's not so bad. That one's obviously pretty short. So here again, I like giving questions that are saying, "Hey, is the tree this property?" Right? But I'm not going to give you like, "Oh, can you test if the tree is complete?" That one's a bit more trickier to do. Here, what we're going to do is, although there is a way to basically do that one, I think, which would be you would have to do a level order traversal, which, again, 90% of tree traversals can be done in order, pre-order, post-order, and the remaining 10% are done with a level order, which has another name, breadth first search, which we'll learn more about later. So write a method given a tree that returns whether the tree is full tree. Remember, that means whether every node has either 2 children or no children. This will be slightly different than the recursive traversal methods we tried so far. And I like this one because it is different. So public, static, Boolean is full, node given, here's the root of the tree. Right, and I just give you one recursive method. I don't have you do those like the public calling the private. I don't have the helper methods here, just simply because Tempest Fugit and Inc. Okay. So first off, standard thing. If root equals null, is the tree full if it has, I don't know. I don't actually know the answer to that one. Is an empty binary tree full?
Full versus complete.
Yeah, but full, let's look at a full binary tree or plane. A full binary tree is either a single vertex or a tree who has root node has two. So no. If so apparently not, but honestly I'm going to go with return. You know what? We can go back and change this if we need it to work, okay? So if root is equal to null, return false. But otherwise, it all depends on, we might not actually need this because it all depends on our children. So first off, once we pass this, we know that the root exists. So first thing what's an easy base case for me? Basically all the conditions where basically I can immediately say I don't have to recurse because I know I'm not full. So if, for instance, root dot left is null, but my root dot right is not null, right? So in other words, if I have something from my left on my right but not on my left, then I know I'm not full. I have one child. So return false. I don't have to recurse. If on the other hand, root dot, and then we can just do the same but reversed. Right? If you have an exam, you can probably do something pithy like same as above but revert, or like now for the flip case or something like that, and I'll fully accept that as an if statement, right? Root dot right is equal to null, right? If we have something on the left, great. Return false, right? What if I don't have anything though? If root dot left and if root dot left is equals null and root dot right equals null. So we're basically going through all four possibilities here, right? As far as what all four combinations of having children, right? Do I have no children? Do I have one of each? Sorry, do I have a left side child? Do I have a right child? And then finally, do I have both children? So, but if I have no children, then I don't have anywhere to recurse, so I'll just simply return true. If I don't have a left child and I don't have a right child, guess what? I have nowhere to go. That's a base case. Return true. My subtree is full. Okay? Now on the other hand, if we go through all these cases and we hit the end, then we're in a bit of a situation here. We're basically where we have a left subtree and a right subtree, which means I'm full, but my children might not necessarily be. And I'm full only if my children are full, right? The full property is that my left subtree and my right subtree are either empty or they both exist, and they are also both full, right? That's what it has to be for every node to have. That's how it works for everything that's tree. For full. Sorry, tired. All right, let's go ahead and so in this case we don't need an if statement because we already know that basically it has to be this last case where I have two children. So in this case, I want to say I'll create a Boolean. I have to recurse here because I have to start looking at my left subtree and my right subtree in more detail. So Boolean left full is equal to is full root dot left. And if you can guess the next line, which is going to be right full is full root dot right. And then what I can do then is just simply return left full and right full. So if both are true, then this statement will be true. Make sense to everybody? And finally, we'll keep that last statement in just if root is null, which we'll only get if the top node is empty. Oddly enough, because of, yes?
Another way we could do this would be like if root equals null, return true, and then an if both sides are null, it'll return true, and then an if both sides aren't null, it'll do the recursive for both, and then return those, and then outside of all that, it just return false otherwise.
I'm sorry, I
Just show you.
yeah, let me see. Let me see what you've got. If tree is null, if tree dot left is null, return true. Right, if tree dot left not equal to null. If they're both. Yeah, you could totally do it like that too.
Okay.
Yep. If it makes sense, then it's probably right. And I like this one because basically when you're having to compare both children, you need these four cases. But still using recursion. Similarly with the equals method. Write a method which, given two trees or subtrees, returns whether or not the contents of the entire tree are identical. In other words, do tree A and tree B store the exact same data in the same exact position? Notice this one's 0 points because it's extra practice. So, public static e Boolean equals.
Wait, I have a question.
Yes.
Should it run the Boolean left full and Boolean right full first? Because it's gonna hit those cases and return true or false.
It's going to return true or false, but but basically what I went through is like, okay, I do all my cases first that I don't care about having to do recursion, right? If root left and root right are empty, awesome. I don't need to do anything. If I have one child or another child, I don't have to check if I have only one child, I don't have to check if that child's full. I'm not full. I am not a full unsatisfied node who has a complete life, so obviously I'm going to return full, right?
I see.
I'm basically trying. Then the point about recursion is basically we turn every decision into a local decision.
I thought you had 4 cases, but the 4th case covers left full, right?
Yeah. So we have an if statement we have an implied if statement over here, but we don't even have to bother writing it because it exists. So node equals. I'm going to go with A and node E B. Is that what I did over there? Yeah, I called them tree A and tree B, and I'll keep with that. Really, I want to name them tree A and tree 1 because I don't want to imply that one's more important than the other, but anyway, so we've got equal. So we've got these two trees, and we want to find out if they are equal. They are the same exact trees. So first off, well, we can't exactly just check if one is null. We actually have to check if both are null. So this actually ends up being very similar to what we have above. If tree A is equal to null and tree B equals to null, then guess what?
True.
Yep, they're exactly the same. Return true. Similarly, this one's fairly simple because I'm just going to copy paste this part a lot. If one of these is
not null, if one of these exists and the other one doesn't, then they're not equal by any sense, right? Right, so we got those three combinations. So now we can finally over here say, wait, they both exist, right? So we have three base cases over here. They exist, don't exist, right? So now what we have to do is that we will have our fourth base case actually. Since we know they both exist, let's go ahead and check, do they have the same values? If tree.a.data not equal, dot equals, right? The dot equals here is the dot equals method, not this equals method that I'm writing right now. Tree b dot data. Although if you did it like this, to be honest, and I'm going to do it like this just for clarity, if tree a dot data is equal to tree b dot data, or let's go with not equals. If they're not, if the data isn't equal, right? We both exist, so I can compare their data now. And if their data isn't equal, guess what? It's not the exact same data, so return false. But otherwise, we know they both exist now, and that the data is the same. So that means we have to compare their left subtrees and their right subtrees, which means that we do Boolean left equals is equal to equals tree a dot left, tree a dot right, Boolean right equals oh, not tree a dot left, tree a dot right, but tree a dot left and tree b dot left. Aha. Then over here, this equals should be comparing the two right subtrees. Tree a dot right, tree b dot right. And then finally, again, we just simply return left equals and right equals. Make sense there? So basically, it's actually, none of these are actually that hard. It's just simply enumerating those if statements out, right? Our base cases. And so figuring out what the base case is kind of essential there. Right? If they're both empty, then obviously they're same. If one exists but the other doesn't, then, which are those next two cases, then guess what? It's false. They're not equal. So now we can check to see if the data is the same because we know they're not null. But if they're not the same, guess what? Don't have to recurse any further because we know the data is not the same. And then finally, if the left side and the right side are equal, then we'll recurse, figure out if the left side and the right side are equal. And if they are, we'll return that. All right, so what other questions do I have? Oof. All right, write a method which returns what characters occur in a string and how many times each occurs. So in other words, doing a character account of a string. What? Is it just making a creaking sound? Okay. So write a method that returns what characters occur in a string and how many times each occurs. So that one is a map, right? Where we're doing a count method. So it's fairly straightforward. We'll need to create a map and return it. Return count. Map character to integer is equal to count. Sorry, called count is equal to a new hash map. Right? So we create a new data structure to hold our count, and then we're going to count every single character. So for string, then to do characters, I'm going to do I'm going to do this as a for each loop. So for character C in, yes.
Could we just do car?
Yeah, I could. For car C in word.toCar array.
It doesn't really matter though, right?
right? Auto boxing and auto unboxing should work for both, although it should work for both.
Wait, I haven't seen that before. Where to char array?
So toChar array takes a string and turns it into an array of characters, so I can use a for each loop over it. You don't ever need.
Would that be listed on the exam?
You don't ever need it.
So we just do like what are we doing and not the two char away, or would we lose points to that?
I mean, we could also do it like this.
Just like a normal.
And we could also do like for int index is for int I is equal to 0, I is less than word.length, I plus plus, char c is equal to char at.
Oh, okay.
So this is just simply a shorter way for me. I am literally using brevity here.
So I think I'm like thinking in Python.
Mm-hmm.
Or like either way with that.
And I use for each loops because I'm big on programming, very similar to how I would do in Python. So basically, we've got two. I'm going to show you a couple different ways to structure this. So first, the normal way to do this is just simply say, okay, if character C, so if count dot contains key C. So in other words, if that character is, if that character has been counted, right? Does that make sense to everybody?
Yes.
If this character has been counted, if it's a character we've seen yet before, then what do? We
The increment. the
yep,
value.
we do int prev count is equal to, and I'm breaking this up into multiple statements, but just for, again, for the ease of reading, is equal to prev count is equal to count dot get C, and then count dot put C prev count plus 1. So we take our previous count, add 1 to it. Yes?
Is there a reason for making that its own emphasize readability?
Yes, that is it. Just readability. Or sorry, no, there's not a reason for it. I will condense it. I'm going to condense this down. I'm going to go back and modify this from basically and make it shorter each time. Okay, but I don't want to start out I didn't want to start out by freaking people out by putting in nested get put statements. Now, what you can't do is do just count get C++, because that's not going to increment it inside, just on the outside. In order to replace what's in there, you have to do the put statement. So otherwise, the count does not contain the key, which means now we've seen it once. So count dot put C, we've seen it once. Okay. If we've not seen it, we get the previous amount of times we see it, and then we increment by 1. So otherwise, and then we return the count. That's pretty much all there is to it, right? If we've seen the character before, we increment the count by 1. Otherwise, we've seen the character once, and so we say so. Another way to do this is, of course, you can just flip this. If it was not, you move this one to the top. And there's a reason I'm doing this, because again, I'm going to be going and refactoring. So you can totally do the if it doesn't contain it first, then put it in. Otherwise, do that. Else. And then we can again condense this statement into one. Since prev count is just count.getC, we can condense this into put C, get the count, the previous count, and add 1 to it. That makes sense to everybody? Another thing we can do, by the way, another way that looks really weird, but think about this, that works, is doing this if we don't like our else statement. If it doesn't have it, put a 0 in. And then, no matter what, get the previous count and add 1 to it. You don't like it? No. It's probably good not to like it because it actually is a bit wasteful because you do a put immediately followed by a get. Put immediately followed by a get and another put, so you have two put operations when it's the first time around.
The get would return 0 if it's not there yet.
So if it's not there yet, we put in 0 and then we get the 0 and add 1. Honestly, though, the first way I like the best, or this way is perfectly fine. Actually, honestly, this way is probably the way I like. They're all. I don't like doing that, but I like showing different ways to do that. I'll skip this question for right now because it's not really relevant to the exam. I just put on something to get people more comfortable with that. How many practice questions here? Yeah. It's not nearly as long, the actual exam. Yeah. So, analysis. So the last page is analysis. What are collisions and hash tables? Why do they occur, and how do we handle collisions? So what are collisions? What is a collision in a hash table?
Same key.
Yeah, so you have not the same key, but two keys want to go where?
It's the same value.
To the same index. Two keys want to go to the same index is a collision, right? So why do they occur? Why do we get collisions in the first place? Because the space of all possible keys is what? What is the space of all possible keys?
Space of all possible keys is as much space as your computer has for, maybe by all possible, but more, so you need to
Yep.
use a smaller array, like the circle.
Yep. The space of all possible keys is infinite. All possible, anything can be a key, right? For instance, if the key is an integer, then any possible integer can work, right, as a key. So what do we need to do? So what do we do? So basically, we have an infinite space of keys, a finite space of where to store them. So obviously, two keys are going to get hashed to the same location. So how do we handle key collisions then? What are the two strategies? The two broad strategies we've learned.
So if it equals a use index, then you want to add 1 to the so if the hash
Yep.
index, like after you determine it by the modulus by the length based on the hash code, if it's equal to a use index, you want to increment the index by 1 in the modulus.
Do you remember what that specific strategy is called?
It's not rehashing.
No, it's not rehashing. It is open addressing. And so that is open addressing, where basically if my space is taken, I'm going to look for another space. We've learned specifically about open addressing using linear probing, which is I'm going to look linearly for my next space, as well as quadratically, which means I'm going to look 1 squared away, then 2 squared away, then 3 squared, then 4 squared. But we mostly care about linear probing. The other way that we learned about, but I didn't implement, was what? It involved linked lists.
Bucket strategy.
Yep, the bucket
Chaining.
chaining. Buckets or chaining is honest. It depends on who's writing the textbook whether they're called buckets or chains. Okay, but yeah, in that case, basically each index can hold more than one item. There are other hashing strategies such as cuckoo hashing. Cuckoo hashing is another strategy, but there's a lot of different ones. It's a scheme for resolving hash collisions of hash functions in the table. Worst case constant lookup time. It derives from the behavior of the species of cuckoo, where the cuckoo chick pushes other eggs or young out of the nest when it hatches. Analogously, inserting a new key into a cuckoo hashing table may push an older key to a different location. So basically, okay, you're in my spot, I kick you out of my spot, and you go to a different spot. Example, the arrows show the alternate location of each key. A new item would be inserted in location A by moving A to its alternative location, which is currently occupied by B, which would move B to its alternative location, which is currently vacant. Inserting a new location into H would not succeed because H is in a cycle, right? H would kick out W, which would kick out H, which would kick out W, right? So it detects that cycle and says, actually, the new item can't go there, so it needs to go to its alternate location. So expected constant time, even with the possibility of having to rebuild the table, as long as the number of keys is kept below half the capacity of the table. E.g., your load factor has to be below 50%, which means wasting lots of space. But hey, we want that constant lookup time. So then you have double hashing, which is resolves half collisions by using we have two different values. It's open addressing, and what it does is that it says, like linear probing, uses one hash value as a starting point and repeatedly steps forward until the desired value is located, an empty location reached, or the entire table has been searched. But the interval is decided using a second independent hash function. So the interval depends on the data. So basically here, we would use a second hash function to figure out, okay, do I want to look one step ahead, or do I want to look every 7 steps ahead, or every 2 steps ahead, or whatever? So there's a bunch of different ways there's been all sorts of different ways, but linear probing and chaining are the basic ways that have been done. Double hashing is actually very popular. But okay, final question. What is the worst case runtime of insertion and deletion algorithms in a binary search tree, and why? Worst case runtime. What's the average case runtime?
Squared and ON.
What's the average case runtime for log n for average case runtime for a binary search tree? Okay. What is worst case scenario? N, linear time. Worst case scenario for a binary search tree is that if I go and if I go across the basically, if I were to insert basically in order 0, 2, 1, 3, let's see, 3, let's see, 5, 4, 6. So basically, just basically looking something like this, where you've got a tree with plenty of zigs and zags, but 20, and let's see, 6, 7, 8, 9. So trees that look something like this, where basically each step doesn't cut it, where it's unbalanced. Each step doesn't cut the amount of space you have to search in half. Each step only brings you 1. It looks like essentially just a linked list diagonally is the worst case scenario. It looks something like this. Right? That's your worst case. In that case, lookup times O of n. And that will happen when it's unbalanced. Now that's pretty rare, but that's the reason we have such things as balanced binary search trees.
The best case just be constant time. Like if you
The
just
best case is always constant time,
Yeah.
but honestly, the average case is log n. The worst case is O of n, unless we're using a self-balancing binary search tree. And those cases, let's see, do I have those slides on me? Arguments, nope. So there are a couple of different strategies for self-balancing binary search trees. For instance, we have AVL trees, which are named after its authors, Adelson, Velsky, and Landis, right? Where its average time and worst case are log n for everything. So here, and what these do is that they work via doing rotations. So if you look at this animation, it keeps track of basically what the balance is on the tree. So it needs to do a left rotation, and it does so. Those rotations, by the way, resolve in log n time. So it takes log n to add, time to add, and log n time to do a rotation, to do a series of rotations. But these rotations, which I'm not going to torture you with this during the summer as an in-class exercise. So that's one way to do it. It works in AVL trees are often compared with red-black trees because they support the same operations. And red-black trees are basically have these rules, and like nodes are either red or black. The root is black. All nulls are black. All leaves are black. And if a node is red, then both of its children are black. And every path from a node to any of its descendants. So any path contains the same number of black nodes. So but basically then what you can do is that if these properties are violated by adding a node, then you're going to end up in one of 5 cases which can be resolved by specific operations. Pain in the butt to program. I know from experience. Another thing, but it works in log n time. Another thing that then you also have 2-3 trees and 2-3-4 trees. So a 2-3 tree is a special tree in computer science where every node has either a 2-node or a 3-node. A 2-node, regular node. 3-node works like this though, where we have 2 values in the node. Everything less than both the values goes to the left. Everything greater than both the values go to the right. So what goes in the middle? Not equal, but very good guess. I'll give you a hint. A is less than B. Yep, anything between A and B goes in the middle. So basically you have, these are nodes with 3 children, and basically you just pretty much searching is pretty much the same. If it's less than the values, okay, then check if you're between these 2 values, check if you're greater than both the values, and then figure out which way to go. And what you do is that when you insert a node, right over here, insertion into a 2 node, right? What we do over here is that if we want to insert 4, right over here, then what we do is we just add it to over here, this node. If we insert into a 2 node, if we want to insert initial, what node needs to be added here? Say we want to insert 10 in this case, right? We temporarily pretend that basically we inserted over here. And then we burst it and we pop it up. So what goes over here is that we move the 6 and the 9 over to the top. And then we move that middle value into the center. This is irrelevant for the test, but if you're in this case, then you can go ahead and insert it and it builds up. So it builds from the bottom down, from the bottom up. But it's just one strategy. There's also a 2-3-4 tree, right, which works exactly the same way as a 2-3 tree, only with 3 elements there. A lot of trees, though, that are B trees, though, is the unlike other self-balancing binary search trees, it's suited for storage systems that read and write relatively large blocks of data, such as disks. So it's commonly used as the basis for a file system. And so that's typically used for file system, or has been. File systems, MS-DOT simply used FAT. So uses a modified B+ tree. Apple's file system HFS Plus and Microsoft's NTFS, and some Linux systems use extension 4, use B trees. So your file system is a tree. It's very obvious if you're using a Unix-based computer. For instance, CD root, that stands for root, and then my file system. Here are all the folders in my root directory. It's your directory status. Your directory structure is a tree. with each folder basically containing its children.
What's the big difference between ext4 versus NTFS?
I don't know. They're just because they're different implementations and have different ways of handling things. I mean, also Linux is nice in the fact that they can just kind of say, we've got a new thing, everything, don't use the old thing anymore, whereas Microsoft has to deal with reverse compatibility issues like crazy.
But then this is where things get tricky. The BRTFS
Mm-hmm.
system.
I don't know too much about file systems, to be honest. I only know I can only really know like the basics about file systems and that stuff I know enough to know that basically that I know enough not to get me in trouble. I know enough to avoid trouble, essentially. But well, anyway, I want to give you time to tidy up on the final bits of assignments, but that's what I have for you guys. I'll be sure to post this and upload this when I get home or stuff.